record the meeting, please? Okay, thank you everyone for joining the Geodesy webinar. And today our speaker is Wenbin Xu from Central South University in China. So the topic Wenbin gonna bring is geodetic image of the Turkey earthquake. And Wenbin received his bachelor and master degree in geodesy from Central South University, where he's currently working at. And he did his PhD in geophysics from the King Abdullah University of Science and Technology. And he worked at UC Berkeley, then the Hong Kong Polytechnic University. Then he joined the faculty. In 2019, his research focused on using INSAR to study crustal deformation associated with a variety of geophysical and anthropogenic processes. So Wenbin, I'm gonna hand over the time to you. Thank you very much.
Okay, thank you, Yao, for the kind introduction, and the president of AGU Geodesy section, Annie, for the invitation. Hello, everyone. I'm Wenbin Xu from Central South University. I'm very pleased to present our latest work on the application of space geodesy to study the earthquake cycle deformation associated with the 2023 Turkey earthquake doublet. I believe many of you are familiar with these events, so I will begin with a brief overview of the seismotectonic setting and the earthquake sequence. Turkey is characterized by complex plate interactions and frequent seismicity. The southwestward lateral extrusion of the Anatolian plate is accommodated by two major faults, the East Anatolian fault zone and the North Anatolian fault zone. On 6 February 2023, two major moment magnitude larger than 7.5 earthquakes struck southern Turkey, causing over 60,000 fatalities and severe damage. The first event with moment magnitude 7.8 with a rupture of 350 kilometer long. And the second event, moment magnitude 7.7 earthquake with a 150 kilometer rupture occurred 9 hours later. Both events produced significant co-seismic slip across multiple fault segments. This highlights the importance of earthquake research. Earthquakes are the rapid release of internal energy causing crustal shaking and deformation, such as surface ruptures and landslides. They act as a natural laboratory for studying earthquake interior structure, geodynamic process, and the earthquake generation mechanisms. This video shows fault motion during the 2025 Myanmar earthquake, where significant ground shaking and deformation can be clearly observed. The occurrence of the earthquake follows a periodic pattern. During the interseismic period, the crust deforms elastically to accumulate strain that will be released in the subsequent earthquake. These periods can last for thousands of years. Monitoring interseismic deformation helps assess regional seismic hazards. Earthquakes generate significant ground deformation, which provide a snapshot of the earthquake source and the energy release. Studying a co-seismic deformation allows us to estimate the fault geometry and the kinematics of the earthquake process. An earthquake lasts from a few seconds to minutes. The fault then enters the post-seismic period, during which stress redistribution causes post-seismic deformation. This deformation allows us to explore Earth's rheology. INSAR, interferometric synthetic aperture radar, known as INSAR, is a space geodesy technique that measures line-of-sight surface deformation using phase differences between satellite images. It is very sensitive to small magnitude deformation. In terms of larger deformation, we can use pixel offset tracking method to retrieve horizontal displacement using amplitude data. By combining INSAR and the range offset measurements, we can get a complete 3D displacement. Therefore, INSAR offers numerous advantages for studying crustal deformation. It provides wide swath coverage of about 60,000 square kilometers for Sentinel-1, and which is ideal for tectonic studies. It has a dense spatial resolution, better than 10 meter per pixel, and a millimeter level displacement measurement accuracy. It supports long-term observation and abundant data for deformation time series analysis. I think it's very particularly valuable because tectonic activities often occur in remote regions with limited conventional monitoring methods. Because of these advantages, INSAR have been widely used to monitor crust deformation such as earthquakes, volcano activity, and land subsidence. However, INSAR also faces several challenges. Let us look at the components of the interferometric phase. So an interferogram consists at least 5 major contributions, whereas we are only interested in tectonic deformation. Unwanted signals such as DM errors, atmospheric delays, and loss of coherence can significantly degrade the quality of interferogram, as you can see from these two interferograms, making high precision deformation monitoring difficult. This is particularly problematic when studying large earthquakes, such as the Turkey earthquake doublet. These two interferograms show severe decorrelation caused by large deformation near the fault associated with the Turkey earthquake doublet. This means INSAR cannot resolve deformation in these regions. However, in practice, many researchers still perform phase unwrapping over these regions in hope to obtain a complete coseismic deformation field, which leads to the underestimation of coseismic deformation or introduce errors in slip inversion. In contrast, the range of sets in the lower left of the Sentinel-1 data can better capture the larger magnitude deformation near the ruptured fault. Therefore, to deal with the phase unwrapping problem in C-band data, we propose an improved snafu phase unwrapping method. It used a range of sets gradients as a prior constraints to update the cost function in low coherence regions. So the traditional snafu method construct a PDF, construct a conditional PDF for each unwrapped phase gradient, and then estimates the most likely unwrapped solution. But it only relies on local phase and coherence to estimate the mean value of the PDF, which can be unreliable in low coherence the regions, such as close to the fault. So our PSNAF method addresses this limitation by introducing range of set gradients as a prior information to better constrain the mean value, providing a more robust initialization and significantly improve the unwrapping accuracy, especially in areas with low coherence. So the workflow of this method can be divided into 3 steps. First, we apply medium filtering on homogeneous pixels to reduce the speckle noise in range offset measurements. Second, we perform prior gradient refinement, which distinguish between the near field and the far field regions through silencing extraction. Third, we conduct a prior guide phase unwrapping. In low coherence areas, the range of set gradients is used as the mean of the cost function, whereas in the high coherence regions, so we can see the fringes in these regions, the original interferogram gradients will be preserved. So the final unwrapping result is then obtained by combining this adaptive strategy in SNAP-FU. So we use this method to unwrap the co-seismic interferogram and compare with the traditional MCF and the SNAP-FU method. As we can see, both the traditional phase unwrapping methods show significant unwrapping errors and underestimate the co-seismic deformation in near the fault. In contrast, our method, the PSNAF method, achieves successful unwrapping across the entire Sentinel-1 co-seismic interferogram without obvious artifacts. Let's take the EKZ1 GNS station, which is located near the surface rupture as an example. So the difference is, so in this here, you can see in this figure, the difference is in the loss deformation between the GNSS measurement and our PSNAF-FU results is only 14 centimeters. But if you use traditional methods to do unwrapping, the difference can reach to meters. Therefore, the displacement from our unwrapping results also show the closest agreement with the other GNS stations. This demonstrates that PSNAF-FU agrees well with the GNSS observations and verifying its high unwrapping accuracy. Let's take a look at the profiles. If we draw some profiles across the deformation regions, we can see the comparison between different unwrapping methods across the fault. For profile BB, which cross this GNSS station, we can find the traditional methods are indicated by the orange and the green line, suffer from extensive phase unwrapping failure within 50 kilometers of the fault. In contrast, our method, PSNAF-FU, the orange line, the red line, successfully recover the fine-scale phase information in near the fault region, producing continuous and complete deformation results. When we compare with the range of set results, you can see our PSNAF method show a stronger robustness against this high-frequency range of set noise. You can see from some profiles. Therefore, combine. Can you still hear me? Okay. Combine this unwrapped interferograms from different orbits, we can generate the 3D co-seismic deformation map of the 2023 earthquake doublet. Can you still hear me?
Yes, yes.
Yes. Okay.
Sounds all good.
Yeah. Okay. As can be seen from this, so we can generate the 3D displacement map of this earthquake doublet. As we can see from the 3D displacement map, both events were dominated by left lateral strike slip motion. So here the east-west component, we can see the blue color indicates the ground move to west. The red color indicates the ground move to east. So it's a left lateral strike slip motion. Okay, we can combine the 3D displacement map with GNSS data to invert for the source model. So the slip distribution model shows the peak slip is close to 9 meters on the Parsec fault segment and the Cardic fault segment. And we can identify a series of asperities at depths from the surface to 16 kilometers along the fault. So this sleep model raises several important questions, and we focus on two key ones. Is a fault sleep predictable on this largest co-seismic sleep segment? That is, what sleep rate and over a given duration would generate a co-seismic sleep of this magnitude. And why did the circle segment which structurally the circle segment which structurally connects these two ruptured faults and underwent significant co-seismic Coulomb stress loading remain unruptured during the earthquake doublet? To address these questions, we use block modeling and a 2D screw dislocation model to investigate the interseismic kinematics of the East Anatolian fault zone and its relationship to the earthquake doublet using geodetic data. So using the published GNSS dataset from Kurt et al. 2023, we perform Euler vector clustering analysis and find that three clusters reveal two boundaries matching the ruptured branches. We then integrate the GNSS datasets into the Arabian reference frame via a 5-parameter transformation to improve the near-fault density and unify inside the published inside velocity field to the same frame using plane fitting. With the block model and the screw dislocation model, we determine the fault slip rates and the interseismic coupling distribution for both fault branches. Both the block model and the screw dislocation model show that the slip rates of the Pacific segment is in a range between 6.3 and 7.4 millimeter per year, while the Cardiac segment has a slip rate of about 2.4 millimeters. This shows that the two fault branches share the relative motion between the Arabian and the Anatolian plates at a ratio of about 3:1. Our geodetically derived slip rates are more consistent with geological rates obtained from field studies when comparing with the other published results. We use the fault slip rates to estimate the timing of the latest prior earthquakes and compare the results with historic seismic records. As you can see, the Pacific and the North Amanos segments on the main ruptured branch are widely accepted to have ruptured in 1114, indicated by this red dot, and the blue dot 1513. Our results show the interseismic slip accumulation matches the observed co-seismic slip very well, about 6 meters for the Pacific segment and 4 meters for the North Amanos segment, indicating slip predictable behavior for the main branch. For the secondary branch, which has a poor constrained historic seismicity, we found two most cited rupture dates, 584 event and 1544 event, based on documentary evidence. The co-seismic slip on the Cardiac segment significantly exceed the accumulate slip since the last rupture if we take these 2 days. So using the slip rate and observed slip, we estimate this segment's last earthquake occurred around 837 BC, close to the medium paleoseismic estimate of 1195 BC from the trenching studies. From the interseismic coupling model, we can see
the co-seismic rupture consistently occur in highly coupled segments. Along the main branch, we identify a creeping section in the northeastern segment. This is consistent with the published work. And on the secondary branch, we find the circle segment is weakly coupled. This likely explains why it did not rupture despite the Coulomb stress loading from the first MW 7.8 earthquake. Another possible reason would be it is still in the post-seismic recovery period following the 1986 earthquake doublet. So, okay, now let's look at the post-seismic deformation of this earthquake doublet. So the previous studies have demonstrated that after sleep can feed the early post-seismic deformation data. However, the far-field post-seismic deformation extends beyond the range that cannot be accounted for by after sleep alone. So a common limitation in the prior studies is the neglect of viscoelastic relaxation. This oversight could result in the overestimation of after-sleep magnitude. So we collect 1 year of 59 GNSS data and INSA data from 3 different orbits to study the post-seismic deformation. So our data includes the sites in Israel and central Turkey, which is located far from the epicenter. To isolate the post-seismic deformation, the signal in GNSS time series, remove the interseismic trends and the periodic signals using the MIDAS methods and combined with the least square approach. Working with the post-seismic signals present significant challenges as evident from these selected. I just randomly select 5 post-seismic interferograms. First, the post-seismic signals are dominated by severe atmospheric noise, as you can see from these interferograms. Basically, we just see atmospheric noise, which manifests as chaotic color patterns across the interferogram. Second, the actual post-seismic deformation signals are extremely subtle, making it difficult to distinguish them from its background noise. To retrieve high accuracy post-seismic deformation time series, we propose a GNSS prior constraint logarithmic decay-based INSA method. In this method, we estimate the uniform decay coefficient using the GNSS data and treat atmospheric and orbital errors at each star epoch, acquisition epoch, as error terms. The deformation phase is parameterized using the log decay model with GNSS derived top. Using under the Tikhonov regularization, the post-seismic deformation time series and orbital errors and tropospheric delays are separately solved from the post-seismic interferograms via nonlinear least square fitting. Here we show a comparison between our new PLOC method with the traditional spatial temporal filtering approach for post-seismic deformation time series analysis. As we can see, the raw INSA time series are indicated by these black dots. Black lines are contaminated by high-frequency fluctuations. And even after spatial temporal filtering, the traditional method indicated by this blue, you can see we can still see significant fluctuations remain in some days. in some days. In contrast, our method, these red dots, produce a much smoother and more robust trend, which closely matches the GNSS observations indicated by these gray dots. We achieve, for this data set, we achieve 23% improvement in accuracy, reducing the RMS from 13 millimeters to 10 millimeters. This demonstrates that the PLOC method not only enhances the accuracy of deformation monitoring, but also enables a more reliable reconstruction of the post-seismic deformation history. Therefore, we apply these methods to the other two orbits. So the results show that the post-seismic deformation covers an extremely wide area, extending from hundreds of kilometers from the epicenter. Specifically, the INSA results reveal a maximum deformation is located about 10 to 50 kilometers from the fault. The post-seismic deformation from the 2D displacement map, we can see the post-seismic deformation is dominated by horizontal motion with a maximum east-west displacement of 13 centimeters. And the post-seismic vertical deformation show a distinct four-quadrant pattern. We also observe a larger vertical deformation amplitude on the eastern side of the Eastern Anatolian Fault, as you can see from both the INSA and this GNSS station. These three primary mechanisms that drive post-seismic deformation, which are crucial for understanding how the crust and the mantle responds to large earthquakes. These three mechanisms are clearly differentiated by their location, physical origin, time scale, and spatial extent. Therefore, we first perform single mechanism modeling for poroelastic rebound, viscoelastic relaxation, and after sleep. As we can see from these results, a poroelastic rebound that simulates deformation driven by fluid pressure changes in the crust. It produces a four-quadrant vertical deformation pattern, but underestimates the horizontal deformation indicated by these arrows. So basically, you don't see horizontal deformation. And after sleep represents the continued sleep on the fault plane. It captures the main feature of horizontal deformation, but underestimate the far field deformation. So basically, you don't see arrows in the far field. And its vertical deformation pattern is inconsistent with the observations. Viscoelastic relaxation, which performs best and recovers the first order features of the 3D post-seismic deformation, significantly underestimates the near field deformation around the fault. Therefore, no single mechanism can simultaneously account for both the near field deformation and the far field deformation. So we seek a combined model to fit the observed deformation. Our modeling strategy is to use the far field GNSS observations to constrain the viscosity of the mantle, and then combine with the near field INSA displacement time series to determine the relative contributions of the lower crust visco elastic relaxation and after sleep via a grid search. Our combined model shows that the Arabian plate compromise a strong crust underlined by an uppermost mantle layer of about 25 kilometers thick with a transient viscosity of 8 × 10⁻⁴ 18 Pascal per second above a weak upper mantle. The viscoelastic relaxation of the upper mantle layer improves the fit for the far-field GNSS stations. The anatonium plate shows a cream brulee type rheology with a stronger upper crust overlying a weak lower crust and a weak upper mantle. So after sleep, is concentrated mainly down deep from the coseismic rupture zone, and a strong spatial complementary is observed among coseismic sleep, after sleep, and aftershocks. The combined model shows the most. So we we compare this combined model with the single mechanism forward model. So we can see the combined model shows the most detailed deformation pattern at the and that closely match the observation. In this model, the upper mantle viscoelastic relaxation explains the far field deformation. After sleep acts in the near field. The RMS misfit between our preferred model and the INSA data is about 1.4 centimeters. That demonstrates the reliability of the model. So to conclude, I want to highlight space geodesy is a powerful technique for studying earthquake cycle deformation. However, we must be careful with various noise sources, such as atmospheric effects during the interseismic and postseismic periods, when deformation signals are small, and face unwrapping challenges for large coseismic deformation events. This is also a problem for the interseismic and postseismic period because the deformation is also very small and the coherence may not be good. So for the first 7.8 event follows a sleep predictable behavior, whereas the second event shows either sleep predictable characteristics or longer interval seismic gap rupture. So the inhibited rupture propagation on the circle fault is likely due to low coupling, and the post-seismic deformation is dominant by viscoelastic relaxation and after sleep. So the East Anatolian fault zone has a lateral heterogeneous rheology. Finally, I would like to express my gratitude. I'm deeply honored to receive the 2025 John Wall Early Career Award, and I would like to thank my graduate students and collaborators for their invaluable support and the insightful discussions, as well as NSFC for the funding support. So if you are interested in our work and want to join our group, please feel free to get in touch. Thank you very much for listening. So yeah, that's all for my presentation.
Thank you very much, Wenbin. That's a very great and a very comprehensive work. So now I'm turn on the chat and the audience can ask questions. Just unmute yourself or put your comments in the chat window. Yeah, thank you very much, Wenbin.
Yes,
And
thank you. So I'm
congratulations
happy
on
to take questions.
for the John Wall Early Career Award.
Yeah, thank you very much for your very interesting talk. I have maybe a first question, just maybe the time that people come in and ask you additional questions. So I've seen that you to extract the post-seismic deformation. So you showed a new method that seems to be quite powerful, and I was wondering whether you had tried, for example, independent component analysis approach, and if this would be also similarly powerful or not.
Thank you for the question. We one of my PhD students actually he has been working on ICA to extract the tectonic deformation from the interferograms. We focus on interseismic, which is very similar to post-seismic interferograms because the deformation is very small. But somehow we work on the another fault, but still we face lots of problems because for the ICA, it's difficult to determine so how many independent components we should have, maybe five, three, and the signals somehow it's mixed. Just maybe two signals, two components will have similar signals. So this kind of mixed signal is still very difficult to use ICA to separate. So that's for our experience, but maybe
Yeah, it's
the
not
audience
easy for
can have.
everyone.
So we are still trying to figure it out. But in some cases, like we also use ICA to study some localized deformation, such as the deformation associated with dam deformation. So the mechanism is more clear. So we know there are about four major mechanisms for the dam deformation. So we can separate and find the best. Which one is the major cause of the deformation. But for these tectonic events, we still don't have a good results.
All right, we have a question by Jeffrey Müller, but maybe the hand raising doesn't work. Sorry. Jeff, do you
Hi.
want to?
Yeah, so I hope you can hear me. I can't start the video, but that's fine. I found it very interesting how you are bringing in some a priori information for the uh, from GNSS or other sources, both in the unwrapping and in some of the analysis of the time series. And I think it's interesting to see maybe very and also potentially very powerful to do this. But there's then becomes some potential issues. So one is, for example, if you use a priori information from some source in resolving the ambiguities that come from, for example, unwrapping, then it's difficult to, it's no longer independent to check against that kind of information. And the same thing sort of might apply in some of the time series fittings. So what are your thoughts about how we can best use this kind of information and then still have a way to test whether we have done it correctly? I think, as you showed with the unwrapping, some of the previous methods did unwrap, but they didn't do it correctly. And so there should have been ideally some better uncertainty information that captures that. So maybe, how do we make sure we are best using this external information for unwrapping or other kinds of fitting for INSAR? And then how do we make sure that we're getting a proper uncertainty that really captures what the uncertainty in that process?
Okay, thank you, Jeff, for your question. So I think you are talking about maybe like these slides, the phase unwrapping for co-seismic interferogram. The uncertainty evaluation, yes, I think that's a very good question. So for our work, we compare with GNSS data, but of course, the range of sets has a very large uncertainty, as you know. So we in our method we did some filtering in our method in order to reduce this kind of noise. And for the far field side, where we can see clear the fringes and the good coherence, we just use the phase information to do unwrapping. But in the large magnitude deformation regions, we use the PSNAF, the rate of set gradient to help to replace the mean value in SNAFU to do the phase unwrapping. But yes, we with more GNSS data, I think we should be able to to quantify the uncertainties. I hope this answers your question.
Yeah, actually, I think yeah, so actually in your unwrapping, you're really still just using only information that's in the INSAR interferogram itself. You're not bringing in anything separate, but you're using it in a different way than the previous approach. Is that correct?
Yeah. Yes.
Yeah, thanks. I think it's very nice to see, and I think your panel F there really illustrates some of the potential downfalls of methods that we have traditionally used. Because if they get the unwrapping wrong, we simply have a big bias, and you only see it when you compare to independent data.
Yes, that's when I review papers. Because now in some people can just use the open source software to do the process. So I often review papers and see these kind of results, and they do immersion, and they say, okay, you see SSD, but that's in reality your data is not correct. So I would like to bring this up to draw people's attention. So you should be very careful when you work with the INSAR data. You don't just run and get the results, but you have to be aware of the error terms that you see in this interferogram.
Great, thank you.
Thank you, Jeff.
Thank you, Jeff and Wenbing. So we have questions from the chat. Kang, do you want to unmute yourself?
Yeah, I will follow up on the previous discussion about the face unwrapping. Wenbin, you showed that looks like with the prior information from the range offset, you are able to unwrap the face relatively more stable, more reliably, even close to the fault, where the correlation is expected to be very low. Do you think if for the regions that have very low coherence, the phase unwrapping is still meaningful with the aid from the range offset?
I'm sorry, your last sentence.
Last sentence was that because in INSAR, when the phase is when the coherence is very low, we expect the phase is more or less random, right? Because but you are able to unwrap that no matter what. So do you think the unwrapped phase is still meaningful in a low coherence region, very low coherence phases?
In the
Do you
low
think
coherence. Okay. Thank you for the question. So the coherence is kind of indicator of the quality of the interferogram. So if the coherence is low, meaning the quality of the fringes is not good. So if you use phase to do the unwrapping, of course you don't get reliable results. But here we rely on offsets. Offsets use the amplitude information which is independent of the phase. So it's just like a cross correlation of these two amplitude data to get the displacement. So the accuracy is lower, but it can help to resolve the large deformation in low coherent regions.
Yeah.
So it can be
let me ask the question another way. Let's say in a region where the correlation is extremely low, the phase looks random, and with the help from the range offset, are you able to retrieve the map of the deformation from the phase?
Oh, you mean the deformation is small, but and also the
No, for example, as you show on the map to the right, the phase looks pretty random because of the low coherence. Are you able to retrieve the continuous map of deformation from the interferometric phase?
This is similar to this earthquake doublet, Turkey earthquake doublet. So we don't see fringes in these red regions. So we can still use our method. You can see it from the figure E, subpanel E. subplot E, you can see our results can resolve, can do the phase unwrapping. And we also apply these methods to the 2016 Kumamoto earthquakes and the ridge crest earthquakes, and we can still get a good result. So we also share this method in Zenodo. So we hope people can use and improve this method.
Okay. Yeah, I guess what I can maybe email you later on to further discuss about this question. My next question is I tapped in the chat, but I'll just rephrase that again. So for the post-seismic modeling, I think you skipped a lot of details. But my question is for the stress-driven upslip, which I believe is what you refer as SDA. Does the result dependent on the parameters or the method you used for the stress-driven modeling? Because the upslip contribution seems to be very modest from what you showed.
Oh, you mean the stress-driven model, stress-driven upslip?
Stress-driven upslip. It looks like the upslip is very minimal or very modest, at least. But my question is, does the magnitude of the SDA dependent on the method or even the parameters that you used for the upslip modeling?
I think this probably in the modeling we use 5 MPa for the A minus B times sigma, and we search for with 0, and there are probably a trade-off between our because this is a combined model, so there are probably a trade-off between our viscoelastic relaxation model.
Yeah, that's actually
Yes.
what I'm trying to ask.
Mm-hmm.
Yeah.
Yeah.
Thanks for clarification.
Mm-hmm.
Thank you both. We have one more question from the chat. Mohammed, do you want to unmute yourself? The questions are on the P snafu model in blind fault nature.
Yes. Hi, Professor Chu. Thank you for your wonderful presentation. My question is concerned about Bisnafu model. What about the Bisnafu model efficiency in blind fault? There is no surface rupture. What is the efficiency of this model for unraveling?
Okay, thank you, Mohammed, for your question. So the goal of this method is to unwrap large deformation or very dense interferometric fringes as seen from the interferogram for cold seismic deformation, especially for the large earthquakes. So if it's a blind fault, that normally produce concentrate fringes at the surface because the surface, the fault did not reach the surface. Then you don't see the fringes will be different. So in my opinion, for blind fault, the fringes will be if it produce very significant deformation, then you can use this method. And but if the deformation is not so significant, then probably this method may not be very reliable because we need the offset. So if you cannot get the range of offsets, then you cannot use this method.
Thank you, Professor.
But in that case, you can just directly unwrap the interferogram and use the other methods because the traditional methods can do very well in phase unwrapping if the deformation gradient is not so severe.
Okay, thank you.
Thank you. More questions from the audience? Just feel free to unmute yourself.
Yeah, maybe I have a last question. So when you showed the model, the viscoelastic model and the poroelastic model, it was striking to me that those models were showing a similar feature in the vertical. So the poroelastic rebound and the viscoelastic relaxation model have a similar vertical, and this is a bit strange to me. And so I mean, depending on the parameters that you use and the depth of the viscoelastic layer, this might change a little bit. And so I was wondering, in the end, you discard, if I understand well, the poroelastic rebound, and you keep a model that accounts for viscoelastic and after slip, if I'm not mistaken. So what guided you in your choice in the end?
Yeah, initially we just compare this single mechanism forward model. So as you can see, this is the results. We think elastic rebound cannot be ignored, but the contribution in compare to this the other mechanisms is the I mean the it's not so significant in comparing to the other mechanisms, but we cannot ignore it. Ignore the contribution from poroelastic rebound. But to do the forward modeling, we cannot combine these three mechanisms. This makes the modeling very complicated. But the contribution from poroelastic rebound is the minorest. That's why
Yeah.
we just
Okay.
use the
So
combined model.
if I remember well, in the case of Landers earthquake, there was a study that was looking at poroelastic rebounds in INSAR data, and so in addition to the large scale features that are visible in the INSAR data, it was possible to see narrow features in releasing band areas or fault complexities. And I was wondering whether you are able to see these kinds of features along the rupture. Do you have a near field signal that might be associated with fault complexity?
In our case, if we zoom in, I think we can see this poroelastic rebound is many effects, as you mentioned, just very close to the fault, especially where faults have the complexity bent or like this. So this shows in our results. Actually, I should show another slide because we compare our results with the three other major events, just like you mentioned, Landers, Hector Mine, and the Ridge Crest. And we can all see that they all use the combined model with viscoelastic VR model and after sleep. But without the poroelastic rebound in the combined model. But the poroelastic rebound does exist. Yeah. But
Sure.
just we don't combine in this complicated model.
Thank you. Yeah.
Yeah, that's our choice. We don't completely ignore it, but we prefer, okay, these two mechanisms can explain. So the misfit probably we can use the misfit to estimate the poroelastic rebound model.
Okay.
Thank you.
Thank you very much.
Yeah, thank you.
Any more questions?
I think we can probably close. Yeah.
Then we can wrap up. Yeah, thank Wenbing for the great presentation, for showing your work. And thank you for the participants from the audience and asking very good and a lot of questions. Yeah, thank you. So this meeting is recorded and will be uploaded to the AGU Geodesy website, so people can watch it again or recommend to your colleagues and friends. Thank you very much.
Thank you very much. Bye bye.
Bye bye.
Yeah.
Bye, everyone.
Bye bye.
Thanks for joining.
Hope you have time to visit China. Oh. Stop sharing.
Yeah. Thank you, Wenbing.
So I can leave the webinar.
Yes, yes. I hope you can sleep
Okay.
tight. It's very late for you already. Yeah, thank you so much.
Okay. Bye bye. Bye bye. Bye bye.
Bye. Yeah, thank you.
Bye bye.
Bye, everyone.